So what we're going to do in this video is we're going to work through example 15.9 in your book. This is one of the first problems that we're going to solve on impact. And what we have here is we have a bag A that weighs 6 pounds, and it's being released from an angle of 0 degrees, and it's 3 feet above box B, where it's going to eventually impact it. And we need to figure out what the final velocities of A and B are after bag A impacts box B. Okay, so we have this bag. You can see it's going to be starting at this horizontal position at A, and it's going to swing down. It's going to eventually strike B. And if you look at this problem, you should recognize that it's going to strike box B along the line of impact. So the velocity is going to be straight along the line of impact. And box B is at rest. So this is going to be a central impact problem. But before we can start using our conservation of linear momentum, we need to figure out what the initial velocity of bag A is right before impact. We know that box B is 0, but we need to figure out the initial velocity of bag A before impact. So what we're going to use, since we have only conservative forces, we only have a weight, and we can see that the energy must be conserved because we don't have any non-conservative forces acting on our system, we can use this conservation of energy equation T1. So initial kinetic energy plus initial potential energy must equal the final kinetic energy plus the final potential energy. So we can use the conservation of energy, and I've drawn here just the initial, we have initial position of bag A, and then we have the final position of bag A right before impact. I'm going to set my datum up at the initial position. You could just as easily set it up at the final position, just a matter of preference. The only force we have acting on our body is the weight, so we have our 6 pounds, and the vertical distance between the two conditions here is 3 feet. So if we plug in our values, our initial kinetic energy for the bag is 0. Our initial potential energy for the bag is also 0 because I set my datum at the initial position. My final kinetic energy for bag A is 1/2 mv squared, so it's 1/2 the mass of 6 divided by 32.2 times the velocity, which is VA squared. Now our potential energy for our bag is going to be minus 6 times 3 because now I'm below the datum, so it's a minus 6 times the distance between the datum and the final position, which is 3. So solving for VA, we solve for it to be 13.9 feet per second, and this is going towards B, so it's going to be directed to the left towards B along the line of impact. So now the next part of this problem is, this was like our little initial problem using the conservation of energy to solve for the initial velocity. Now we're going to actually be able to use our conservation of linear momentum between the bag A and the box B in order to figure out what the final velocities are between A and B. Okay, so what I've drawn here are some momentum diagrams, and you can see that before impact we have the box that has a momentum of 0, so we have 18 divided by 32.2 times 0 has no initial momentum, and the momentum of the bag is going to the left, and that's the mass of 6 divided by 32.2 times the velocity, which we had solved for, which was 13.9. Now after impact, we have some unknown velocities, B2 and A2, and we're going to assume they're both going to the left after impact. So we have our momentum, mass times velocities for each of those. So what we're going to use is we're going to use the conservation of momentum to solve for an equation with two unknowns, and then we'll also use the coefficient of restitution to get our second equation. So then we'll have two equations with two unknowns, and then we can solve for our final velocities. So our conservation of momentum equation, we have ma va1 plus mb vb1 is equal to ma va2 plus mb vb2. So plugging in the values, we have the mass of A times the initial velocity before impact of A. The momentum of B is 0 because it's at rest. Then we have the mass times our unknown velocity A2 plus our mass times our unknown velocity B2. Now both these velocities are showing as positive because we assumed a positive direction and our x direction was to the left. And recall that this conservation of momentum is applied along the line of impact. And in our problem, if we go back to our picture here, our line of impact is along this x direction. So we're only counting for those velocities that are along that direction. So next what we're going to do is we're going to put together our conservation of momentum. We're going to be able to simplify this conservation of momentum equation into an equation with VA2 and VB2, and then we'll put together our coefficient of restitution equation to get our second equation. So now you'll see that we reduced this equation down to this equation here. So we have two unknowns in that equation for conservation of momentum. And this is down here, this is the coefficient of restitution equation. So we have our relative separation velocities, so our final velocities, divided by the relative difference between the initial velocities. So we were given in our problem that the coefficient of restitution was 0.5. We don't know these terms in the numerator, those are what we need to solve for, and we know the initial velocity of A is 13.9 and the initial velocity of B is 0. So with these two equations, we can have two equations and two unknowns, and we can solve for VB2 and VA2. So when you work through those two equations with two unknowns, you should solve for VA2 is a negative 1.738 feet per second, and VB2 is a positive 5.21 feet per second. So these directions here, remember, if we go back to our original picture here, we showed after impact they were both going in the positive x direction, which was to the left. But since we solved and we got a negative for VA2, that means that it's actually going back to the right. And VB is, so the box is moving to the left. That's what we're showing with these negatives and positive signs. Now the next part of the question asked, what is the energy loss between during this collision? What is the energy loss in the collision? So what we're going to use for that is we're going to apply work and energy, and we're going to find the difference between the two kinetic energies, the kinetic energy after impact, and we're going to subtract from that the kinetic energy before impact. So in setting up this work and energy equation, we have the sum of the work is equal to our final kinetic energy minus our initial kinetic energy. So I just plugged in the values here, 1/2 mv squared for bag A. So this is the final kinetic energy for bag A. This is the final velocity, plus 1/2 mass of the box times the final velocity of the box. We're going to add those up. and then we're going to subtract the initial kinetic energy, which is all in the bag, which is 1/2 6 divided by 32.2 times our initial velocity before impact, which is 13.9 squared. So our final energy loss, which is defined by this work term, is going to end up being minus 10.1 foot-pounds. Okay, so that is the loss in our system. So this shows that we have an inelastic deformation that's occurring because it turns out to be negative. And that finishes our example for 15.9.